In particle physics, the top quark is famously unstable. Standard models calculate its lifespan at 10 to the negative 25 seconds. That is so brief, it disappears before it can ever form a bound state with another particle. The strong nuclear force, the incredibly powerful glue that normally holds atomic cores together, simply cannot act fast enough to grab these quarks before they annihilate each other and scatter into chaotic debris. But the CMS and ATLAS collaborations at CERN recently recorded a 5 sigma observation that contradicts this expected timeline. Inside this massive detector array, they found evidence of Toponium, a temporary bound state of a top quark and an anti-top quark. To achieve this, researchers looked for a highly specific experimental condition. The quark-anti-quark pair had to be produced practically at rest relative to one another, moving at almost zero relative velocity. This chart maps the resonance profile of that discovery. By dropping the relative velocity of the particles, the experiment minimized internal torsional friction. This allowed the quarks to briefly form a standing wave boundary, a structured shape, where standard models predicted total chaos. The fact that these quarks bond only when their relative motion is paused suggests that the 10 to the negative 25-second decay timer isn't a fundamental property of the particle itself. Instead, it indicates that radioactive decay is a structural failure, an event that occurs when internal energy simply outpaces the capacity of a geometric boundary to contain it. To understand how a structure can fail geometrically, we have to rethink the atom. We are usually taught the planetary model, a visual of tiny, hard spheres orbiting a cluster of slightly larger hard spheres. The problem is, an atom is 99.99% empty space. If it is mostly void, we have to explain why the physical world around us possesses the rigid, unyielding properties of solid matter. This suggests the atom is not a collection of objects, but a highly tuned event, a self-sustaining coherence engine. This framework models matter as trapped light, a high-frequency energy pattern captured inside a geometric loop. Viewed as a spinning energy vortex, the nucleus naturally expands outward, the active mode. To prevent dissipation, the electron shell acts as a standing wave boundary called the connective mode. Stability is achieved when this expansive drive is perfectly contained by the shell's compressive geometry. The solidity we feel in the macroscopic world is the result of this perfect phase locking between internal energy and external geometry. We can apply this balance of forces back to the CERN anomaly to explain why Toponium formed. By producing the quarks at rest, the experimenters removed the kinetic interference that usually prevents a stable boundary from forming. For a fraction of a second, the internal energy and the boundary constraints achieved a stable ratio. This model illustrates that momentary state. You can see the interlocking double helix center and the dense nodal ring where the quarks achieved a geometric phase lock, functioning briefly as a stable, bound standing wave. The CMS discovery provides the empirical evidence for this shift. Atomic stability is a problem of resonant geometry rather than simple probabilistic decay. Currently, we synthesize superheavy elements through brute force bombardment, smashing heavy ions into targets and hoping they fuse on impact. This explains why elements like 118 decay in milliseconds. Kinetic impact forces the nucleons together, but they lack the structural framework needed to contain the massive internal repulsion of the resulting core. To create elements that last, we must use harmonic capture, establishing a predefined stability well using electromagnetic fields before injecting the nuclear material. Moving from observing these states to manufacturing them requires precise control over resonant field geometry. The primary target for this approach is element 126, a hyperstable superheavy element referred to as Coherium. This schematic outlines phase 1, the geometry template. By using high-energy fields, we generate a ghost atom, an energetic blueprint that mimics the dodecahedral electron boundary of element 126. Phase 2 is resonant tuning. As this data shows, tuning the field to a 57.8 GHz lock point allows nuclear plasma to settle into the predefined template without the scattering typical of kinetic collisions. The process concludes with phase 3, the crystalline lock. Pulsing the field at a specific harmonic frequency secures the structure, resulting in the charge stability locked state shown in this registry data. Because Coherium is built within this perfect structural balance, it is predicted to be impervious to standard decay, exhibiting hyperdensity and room temperature superconductivity. This process marks a transition from managing the isotopes we find in nature to engineering materials by organizing energy into specific field geometries. Instead of searching for materials with specific properties, we can determine those properties by designing the stability wells they occupy. By mastering the geometry of resonance, we gain the ability to engineer the fundamental building blocks of matter from first principles.